Hello and welcome to Math 24. My name is Greg Perkins. I'm your host and instructor. Just real quick, you might be wondering why the video is presented in this way where you can see my hand and a pen. Well, I've been making these videos for quite a while, and over the years students have said this is the best way to do it. So I've created them in front of a whiteboard or just with the computer, with an iPad, etc. And students said they really like this way. One of the good advantages is anytime I need to use a calculator, then I can just put it right here and you can follow along. I can show you exactly how to use the calculator and what results you should be getting. Okay, now let's start working on this week. We're doing sections 1.1 and 1.2, and because these two sections are pretty small, I'm going to go ahead and put them together in this lecture. So to begin with, if you have an arrow like this, that's called a ray. And let's say that this goes from A through point B. And then what if you have another ray, let's say going in this direction, that goes from A through C. So this creates an angle, and you could call it angle A, and as long as nobody's confused by that, okay, here's A, and then we would actually be talking about the inside part. Another way to say it is go from B to A and then to C. So B, A to C provides a little more information. Okay, you're talking about this part right in here. Or angle CAB going in this direction still gives you this angle. Well, just like my name is actually Gregory, I don't actually go by Gregory, I go by Greg, nickname or a shortened name. So you can do that here too. So quite often we use this letter right here, which is the Greek letter theta. And usually theta is used for the measure of the angle, like 40 degrees or 45 degrees. And then A is like its name. But quite often we'll just have the theta on there and then solve for theta. So here's some special angles. One is, if two things are perpendicular, then this would be 90 degrees, or you could just put a little square right here at the bottom, and then that is a right angle. If the angle goes straight across, then when you measure this, that would be 180 degrees. And if it was like this, and you were asked to measure from here around to here, that's basically combining these two ideas. So from here to straight across is 80 plus another 90 is 270 degrees. Then some definitions. So an acute angle measures less than 90. So for example, this angle right here, that's approximately 45 degrees. That would be an acute angle. And then an obtuse angle is one that measures more than 90 degrees. So for example, this could be 110 degrees. So that would be obtuse. Then on to some other definitions, this time for pairs of angles. So if you have an angle like this, and this angle, the traditional way to measure it is from here to here. But if you measure it from the top down, you get the same number. Now let's say that you continue this as a straight line, then it actually creates an angle over here. So going from here to here, so each of these angles terminates along this line. So they start and then they stop when they get to the same line. So these are called coterminal. So co means doing the same thing. They co or cooperate, and they're terminating at the same place. Now, because this line right here is a straight line, that means that the two angles have to add up to 180 degrees. So if this one was 35 degrees, then how much would x be? So x plus 35 has to equal 180. Now just subtract 35 from both sides. And here's one of those places where I get to use the calculator. Let me clear out this old stuff. 180 minus 35 is 145. So x is equal to 145. And then technically, I should say that we're using degrees. All right. Here's another important fact that we're going to be using quite a bit. Suppose that you have parallel lines, and it might say the word parallel lines, or it might have these little arrows. It's not an arrow at the end, but somewhere in the line itself, that means that these two are parallel. So they go at the same angle, they would never intersect. Then suppose that you have a transversal. Well, then the fact is that whatever this angle is, this angle has to be the same thing. So by putting the same little arc on each one, that's a way of saying that they're the same. But if this one was 25 degrees, then this one would have to be 25 degrees. These are called alternate interior angles, and they are congruent. Congruent means that they have the same measure, 25 degrees and 25 degrees. So alternate interior angles are congruent. So congruent is a fancy way to say that they're equal in some way. In this particular one, they're equal in measure, 25 degrees and 25 degrees. But if you were to just say that two angles are equal, that would be sort of vague, because do you mean like one angle is here and the other angle is exactly the same? Or do you mean that they're like this? Or do you mean that they're like this? So anyway, congruent means that they would have the same measure, 25 degrees and 25 degrees. Now for an example of that. Suppose that you have, so for example, you have parallel lines, there is a transversal, and then suppose that this one is 2x minus 12 degrees, and this one is x plus 4 degrees. Then the directions are, what does x equal? Well, in the one that I just did, I did this angle has to be the same as this angle. But the same is true for this one on the outside of this transversal as well as this one. So that means that this one has to equal this one. So a 2x minus 12 has to equal an x plus 4. And then I'm going to collect the x's on the left side, so subtract x from both sides. And at the same time, move the number 12 to the right side. So this is just going to be x. These cancel, and a 4 plus 12 is 16. Now another interesting fact about angles is if you have any triangle, and let's say that this angle is, let's see, that one looks like it's about 50 degrees. And then this angle looks like it's about 85 degrees. Then solve for x. So whenever you have a triangle, the three angles will always add up to 180 degrees. Doesn't matter what kind of triangle it is, the three angles always add up to 180 degrees. So if you add those three up, it has to equal 180. So let's see, an 85 plus a 50, that's going to be 135. And then subtract 135 from both sides. And, oh, that's very similar to the last one I did. It equals 45. So then x equals 45. And while I'm doing this algebra, I don't feel like writing down degrees. So I'll just save it till the end. X degrees equals 45 degrees. There you go. Next up, suppose that you've got a clock. And by that, I mean an old-fashioned clock with a big hand and a little hand. And let's say that it's 4 o'clock in the afternoon, because nobody wants to get up at 4 o'clock in the morning to look at the clock. So there's my fancy clock. Now suppose that this is the angle theta. Then, how much is theta? Does it equal 20 degrees? Does it equal 100 degrees? How much? Well, there's a couple of ways to do it. Here would be the fastest, easiest way, and that is if you go around a circle completely, that is 360 degrees. The reason it's 360 degrees is because the ancient Babylonians had a number system that was based in 60, and several thousand years ago, they were the first to come up with this idea, so they used 360. There's 365 days in a year, and the Earth goes around the sun in those 365 days. Well, they knew that, but dividing things into 365 is difficult. With 360, it's easier. You can cut it in half, it's 180. You can cut it into quarters, it's 90. So anyway, one time around a circle is 360 degrees. So for this clock, one time around is 360. But if this is 4 o'clock and there's 12 hours total, so this is 4 o'clock, or in other words, 4 hours has passed out of 12 hours on the clock total. Then when you reduce, that means that it's 1/3. So that means it's 1/3 of a circle. Now I'll just use this idea. What's 1/3 of 360? So 1/3 of 360, a 3 will divide into 3 one time, a 3 will divide into 6 two times, and a 3 will divide into 0 0 times. So that is 120 degrees. Now, just for extra fun, if you want to know another way to do it, you could say for each hour, so here's 1 o'clock, 2 o'clock, 3 o'clock, etc. So since there's 12 hours on the face of the clock, each hour is going to be 1/12. So it's going to be 1/12 of 360 degrees. A 12 will divide into a 36 3 times, so that leaves 30 degrees. Now if that's for each hour, then for 4 hours, it's going to be 4 hours times 30 degrees each one. It's going to be 120 degrees. This is one of the beautiful things about math. You can do something in 2 different ways or even 3 different ways and come up with the same answer. That's the beauty of math. Okay, then on to the next example. Suppose that you have a triangle like this. And then it's got these 2 marks on it. So when it's got these marks, that means those sides are the same. So if this is 15 feet, this is 15 feet. That's called an isosceles triangle. Now, if it had all 3 sides the same, then it's called an equilateral triangle. So an equilateral triangle has all 3 sides the same. So equa means same, lateral means measurement. So they're the same measurement triangle. Anyway, this one is isosceles. It's got 2 sides the same. And now suppose that this is x degrees. This is 60, hold on, I want it to be 65 degrees. And this out here is y degrees. Solve for x and solve for y. So when 2 sides are the same, then the angles opposite those 2 sides have to be the same. This one says 65. I know it looks like 60 smudge, but this says 65. So that means that this one is 65. Now to solve for y, this is a straight line which is 180 degrees. So that means that y plus 65 has to equal 180. Then just subtract 65 from both sides. So 180 minus 65, y is equal to 115. And then what about the x? So inside the triangle, x and 65, they have to add up to 180. So 65 and a 65, that equals 130. And then to solve for x, all I need to do is subtract 130 from both sides. And x degrees is equal to 50 degrees. Now, whenever you see me draw these pictures, they may not be exactly accurate. Like I did not measure this when I drew it, so I don't know if I were to measure it, it's 50 degrees. But the math is definitely correct, even if my drawings aren't perfectly accurate. All right, just one more example for this, or for these 2 sections. And that is, suppose you have a parallel line that's short and a parallel line that's bigger. So I put a little arrow in them to say that they're parallel. And then connect these 2 ends and connect these 2 ends. Makes a crazy looking number 8. Now suppose that this is 55 degrees and this is 50 degrees. Then can you find all of the missing angles? 1, 2, 3, 4. Well, because these lines are parallel and this is a transversal, that means that this angle has to equal this angle. So I don't quite have enough room, but this one is 55 degrees. Another fact that's not even going to use the parallel lines. Whenever you have two lines cross, then this angle and this angle, called vertical angles, they're going to be the same. So if this one is 50 degrees, then this one is also 50 degrees. So that happens right here. So this one across from that 50 is also 50 degrees. And now, since we have this triangle and all three angles have to add up to 180, I could for a moment call this theta, and then theta plus 50 plus 55 has to equal, hold on, I said 50. Why did my pen write 55? Has to equal 180. So a 50 and a 55, that would be 105. And then the last thing to do is subtract 105 from both sides. And then for this one, I don't even need a calculator because the 100 minus 100, those are gone. And then 80 minus 5 is 75. So this one equals 75. And then this one is an alternate interior for this one, interior angle. So that means this one is also 75. All right, we're now done with sections 1.1 and 1.2.